So in the last lecture, we described perception behaviorally. I pointed out that perception is more than just sensory signals. We bring prior information to the problem of perception. And to some extent, this gives us an advantage over perceiving machines, over computer vision systems and speech recognition systems. We've described the problem at the behavioral level. We've described what perception is. And now we want to come up with some theory that captures the behavioral phenomenon that we've described. So now we're sort of tackling the problem at the algorithmic level, if we think about Mars' 3 levels of analysis. So what we're going to do today is review some theories, attempt to explain the perceptual phenomenon we've observed. And we'll start with a historical theory, Gestalt psychology, which you may remember from intro psych, and then we'll move on to sort of more modern views of how the brain does perception. So if we go back to the mid-1800s, Wilhelm Wundt, psychologist interested in reaction times like Donders, he was known as a structuralist, and structuralists argued that perception is essentially the sum of sensation. Clearly this isn't true. We looked at this in the last lecture. Clearly perception is just more the sum of our interpretation of sensory signals. And so in the early 1900s, a group of psychologists got together in Austria and Germany and formed what is known as the Gestalt School of Psychology. And their argument was that perception is more than just the sum of its parts. And this can be sort of shown using this phenomenon, which is called apparent motion. And actually, the Gestalt psychologists were very interested in apparent motion. So what's happening here? Some blue circles are disappearing and reappearing, but the pattern in which they're disappearing and reappearing creates the appearance of motion. We're getting something more here out of the sensory signals that are striking our eyes. We're seeing motion where there actually is no motion, right? If we were just interpreting the sensory signals, we wouldn't perceive motion. In this image, we would just see blue circles appearing and disappearing, but there's something more here. So Gestalt psychology simply means that the whole is greater than the sum of its parts. And what the Gestalt psychologists attempted to do was come up with some principles, some rules for describing how we perceive our world. And there are many different rules that the Gestalt psychologists came up with. I'm going to just review 3 of them in this lecture to give some historical context here to theories of perception. So the first Gestalt principle is known as good continuation, and it suggests that objects that go behind other objects are perceived as continuous. And it's based on the idea that we tend to group lines and curves together if they're headed in the same direction. Right? So you can look at this coil of rope, and the piece of rope that's highlighted in the image on the right here, we perceive that as one continuous piece of rope, and that's because the curves follow the same trajectory. But there's nothing in the sensory signals coming from this image to actually tell us that the rope is continuous. The Gestalt psychologists would say that we are making this assumption based on this rule of good continuation that's sort of hard-coded into our perceptual system. So good continuation is one principle of Gestalt psychology. A second principle of Gestalt psychology is known as simplicity or good form. And the idea here is that we tend to form the simplest perceptual explanation for stimuli that our sense organs are receiving. Right? So when we look at the Olympic rings here, we perceive 5 interlocking rings. Now again, if we're just going by the sensory signals that we're seeing, there's nothing in the image that says that we couldn't perceive this image down here at the bottom of the screen. So sort of 5 bits and pieces of rings. There's nothing in the sensory information that says that, that could be actually what's happening in the world, yet we don't perceive the image like that. We perceive the simplest sort of possible explanation, which is that there are 5 interlocking rings. So this is the second principle of Gestalt psychology, the principle of simplicity in good form. And the third principle that we'll talk about is the principle of similarity. And the idea here is that we tend to group features that look alike together in images, right? So if we look at this image here, we tend to group the stars together because they're the same. And I think these are octagons, again, together because they're the same shape. Groupings can be based on color, size, orientation, and form, but they're typically not based on the conjunction of features, right? So if we take this image here, it's easy to group similarly colored shapes together. So we can see red shapes and green shapes. It's easy to group shapes of the same form together, right? We can see squares or diamonds. It's harder to group together images that are a conjunction of features. So for instance, red squares and red diamonds, or green squares and green diamonds. We don't tend to group those items together. So we group based on single features versus, conjunction, the conjunction of features. So there are more principles of Gestalt psychology. I'm not going to go through them. The idea here was just to sort of introduce this early attempt at putting some theory behind perceptual experience. Now, these principles were thought to be, built in to the perceptual system. And so this presents a couple problems. From the Gestalt point of view, the rule of experience was pretty minor, and these rules were fairly rigid. And as we saw in the last lecture, experience can actually play a huge role in perception. So I played you that demo of noise vocoded speech, where you heard the speech signal that basically sounded like gibberish or noise. I gave you some experience. I played you the unaltered version of the signal, and this allowed you to then perceive the signal with more clarity, to disambiguate this ambiguous sensory signal. So clearly experience plays a role, and clearly having rigid rules, right, is the wrong approach. We want some flexibility here. And the second problem with Gestalt psychology is, when do the rules stop? How many rules are enough, right? How many rules do we need to, capture all of perceptual experience? And this is one of the reasons why I'm not going through all of the many Gestalt rules in great and gory detail. So, not a lot of flexibility in Gestalt psychology, right? It's like you move into an apartment, it's got this like crazy built-in kitchen, you don't like your fridge, nothing you can do about it because it's built in. Clearly that's not how perception works. So let's take a different approach. We're going to look at an approach now that has roots that date back to the 1800s, but it's built on sort of this idea that we're combining sensory information and prior knowledge in a very flexible, probabilistic type of way. And the idea started with Hermann von Helmholtz, who was a German physicist. He worked in several fields, including visual perception. And Helmholtz came up with the notion of unconscious inference. Inference simply means a conclusion based on evidence and reasoning. And in Helmholtz's view, that's what's happening in perception, right? Your brain is unconsciously sort of figuring out, what's the best solution to the problem given the sensory signals that it's receiving and given, prior knowledge, top-down information. So Helmholtz might be interested in this question here. How does the brain decide that there's a blue rectangle in front of a red rectangle in this image, right? So this is the retinal image. This image could be created by B or C. Both can create that image. How does the brain decide? And so Helmholtz would draw on what he called the likelihood principle. And he would say that we perceive what is most likely to have caused the pattern of stimuli on the retina, given sensory signals and prior knowledge. And so in this case, prior knowledge, right, would suggest that it's much more likely that we're simply looking at a red rectangle behind a blue rectangle than we are looking at this sort of complicated pattern of shapes in choice C here. And so in Helmholtz's view, prior experience acts in conjunction with present sensations to produce the most likely perceptual image. And this view has really stood the test of time, and recently, in like the last sort of 20-25 years, we've actually put some mathematics to this view, and we can sort of nicely model how we perceive our world using probability theory and something known as Bayes' rule. And so this approach has led to a field of perception, a view of perception known as Bayesian perception. And I'm going to walk you through this. I'm going to go quite slowly because it does involve probability theory, so there's necessarily statistics and some math. I won't ask you to do math in this course, but you do need to have a conceptual understanding of what's happening. And we're talking about probabilities here. This is an important idea. And the suggestion, right, whenever we're talking about probabilities, the suggestion is that we're never 100% certain about anything. We're coming to some probabilistic conclusion. And it may be, that we're 99% certain, but we can never be 100% certain. So keep that in mind when we're discussing Bayesian perception. So what is Bayesian perception? Again, it's based on Helmholtz's idea of unconscious inference. And the central idea is that perception is the brain's best guess. It's a probabilistic inference. And this inference is based on the available sensory evidence and prior knowledge about the world. So again, I'll just point out probabilistic inference. Probabilistic means that we can never be 100% certain about what we are seeing or what we're hearing. We're coming up with the most likely explanation given the sensory evidence and our prior knowledge about how the world works. So let me give you an example, and this is from a really nice paper by Daniel Wolpert and Conrad Cording that was published in 2004. And so imagine you're playing tennis against Roger Federer, arguably the greatest tennis player ever. You serve the ball to Federer, he returns it. And so you're tracking the ball as it flies towards you, and you predict that it will land somewhere in this red oval here. So your sensory evidence is telling you that the ball's going to land somewhere in that red oval. But you've played Federer a bunch of times before. You know he's an incredible player, and he tends to hit balls that land just along the baseline, right? And that's what you want to do in tennis. You want to hit balls so they land, just in bounds. And so you have this prior knowledge that's telling you that Federer tends to hit balls that land along this green line here. And so Bayesian views of perception would suggest that you combine these two sources of information to come up with the best guess or the most likely outcome given the sensory evidence that you have, saying the ball will land here, and your prior knowledge of playing Roger Federer, saying that the ball will land somewhere in this green area. And so the answer lies somewhere in the middle, right? So in this sort of yellow region here. And indeed, in this paper by Wellport and Cordine, they show that this is actually, when we're tracking movements, when we're performing actions in our world, this is exactly what we do. So we sort of combine sensory evidence and prior knowledge in a probabilistic way to come up with sort of the best guess, best inference about what's happening in our world. So that's sort of the high-level overview of how Bayesian perception works. I'm going to run you through a bit of the math now. And again, you'll never have to do math in this course, but you should sort of understand conceptually what's happening and why this approach is very powerful. So let's step back to what is probability. Probability defined is a ratio between 0 and 1 that describes the likelihood of an event occurring. Stated more simply, probability is the desired number of outcomes divided by the total number of possible outcomes. If I said to you, what's the likelihood that you flip a head if you're flipping a fair coin, you would say, well, I want one outcome, head, and there are two possible outcomes, so it's 50%. If I said, what's the probability that you roll an even number with a fair die, you could say, well, there are 3 even numbers on a fair die, right? 2, 4, and 6. 6 possible outcomes, and so the probability is, again, 50%, or 3 divided by 6. So probability defined, quick review of stuff that we covered in intro psych. Bayesian perception relies on what's known as conditional probability. And conditional probability is simply the probability of one event occurring given that another event has happened. So given that something has happened, what's the probability of an event occurring? So I'll run you through just a quick example, so just to make sure that you understand how conditional probability works. So here's some fictitious data. Imagine there's a relationship between brown hair and heart disease. So we've sampled 2,000 people, and here's our sampled data. 741 people in our sample had heart disease and had brown hair. 160 people in our sample had brown hair and didn't have heart disease. 260 people in our sample didn't have brown hair and they had heart disease. 840 people in our sample didn't have brown hair and they also didn't have heart disease. Fictitious data, just made up, but I think it's for the purposes of this example, please sort of imagine that there is this fictitious relationship between having brown hair and heart disease. So if I asked you what's the probability that somebody in this sample has brown hair, super simple to calculate, right? How many people in the sample have brown hair? 740 plus 160. How many people are in the sample? 2,000. Probability is about 45%. Okay. Now, what's the probability that somebody in the sample has heart disease? Again, super simple. Look at the chart. How many people have heart disease? 740 plus 260. How many people are in the sample? 2,000. Probability that somebody has heart disease in the sample is 0.49. Let's step it up a little bit. So what's the probability that somebody has brown hair and has heart disease? So we're looking for now a conjunction of probabilities, right? So with the data laid out like this, it's pretty easy to see. You can just simply look at the chart. So 740 people have brown hair and have heart disease. 2,000 people in the sample, the probability is 0.37. So hopefully this is fairly straightforward so far. And now we come to the conditional case. And again, the idea here is that you understand how conditional probability works. So what's the probability of having brown hair given that you already have heart disease? So given that something has happened, right? Given that you have heart disease, what's the probability that you have brown hair? And so in this case, we're actually restricting our sample to this column here, right? Because we have to satisfy that initial condition. And this is the nature of conditional probability. And so we simply look at this column here and we say, okay, well, what's the probability that somebody has brown hair given that they have heart disease? 740 people have brown hair out of a pool of 1,000 that have heart disease. So the probability that somebody has brown hair given that they have heart disease is 0.74. So that's a conditional probability. And Bayesian perception is based on conditional probabilities. In particular, it's based on Bayes' rule. Bayes' rule is named after the Reverend Thomas Bayes, who was alive in the 18th century. And the rule allows us to calculate the inverse of a conditional probability. Right? So if we know the probability of B given A, we can calculate the probability of A given B. So if we know the probability of brown hair given heart disease, we can calculate the probability of heart disease given brown hair. And they're not equal. That's the trick here, and that's what Bayes' rule allows us to do and allows us to calculate. So it allows us to find the inverse of a conditional probability. So at this point, you're probably thinking, okay, that's all great. You've thrown this math at me. What the heck does this have to do with perception? Well, perception is really just a conditional probability problem. Okay? So you have this image on your retina, and you want to figure out, given this image on my retina, what's happening in the world? What's the most likely thing that's happening in the world? So Bayes' rule gives us a means to tackle the inverse projection problem. So if you remember in the last lecture, I talked about this inverse projection problem, right? We have this image on our retinas. We're not sure what in the world has created that image. Bayes' rule now gives us a means to tackle that problem. So given this image on our retina, what's the most likely thing that's happening in our world? And it turns out that the answer to that problem is simply a probabilistic combination of the sensory stimuli that we're receiving and our prior knowledge about the state of the world. So just to say that again, we can come up with an estimate of what's happening in the world given some sensory evidence and some prior knowledge about how the world works. So hopefully that's clear to everyone. But the takeaway message here is that, this problem that we face in perception, trying to figure out what's happening in our world based on the sensory signals we're receiving, is simply a conditional probability problem. And Bayes' rule allows us to tackle that problem using math. And it turns out human behavior is actually nicely predicted by this math. So let me show you an example, and if any of this is confusing or unclear, please do send me an email, and I'm happy to walk you through it. So this is an example from the chapter that I asked you to read by Ma, Cording, and Goldrick that's posted on Acorn. And it's known as the baggage claim problem. I think it's a really sort of nice example of how we can view perception, the problem of perception, as just a conditional probability. And so imagine you've gotten off a plane, you're waiting for your luggage with 99 other people on your flight in the baggage claim area. So you're on a flight, 100 people on the flight, you're waiting for your bags. Your bag is quite popular. So your bag looks like 5% of all travelers' bags, right? So there's some ambiguity there. If you see a bag that kind of looks like your bag, there's some ambiguity. You're not 100% sure that it is actually your bag because your bag looks like a lot of other bags. And so here's the question. The first bag comes out onto the carousel, and it looks like your bag. The sensory signals that you're receiving are telling you that it looks like your bag. But you know there are 99 more bags left to come out. So you have to make a decision. Is it actually your bag? And Bayes' rule, conditional probability, allows us to tackle this problem. This is necessarily a probabilistic problem. We're asking, what's the probability that the bag is yours, given the sensory information that we're receiving? And we call this the posterior. So what's the probability that the bag is mine, given the sensory evidence? And it turns out that the posterior can actually be calculated from something known as the likelihood and the prior. So what is the likelihood? The likelihood is just the probability of the sensory evidence if the bag is actually yours. So given the bag is yours, what's the probability of the particular sensory evidence that you're receiving at that time? The prior is your prior knowledge about the state of the world. And so it turns out that the answer to this problem is just a combination of the likelihood and the prior. And again, the likelihood is defined as the probability of the sensory information if the bag is in fact yours. The prior is the probability that the bag is yours based on everything else you know, based on all your prior knowledge, right? Based on this idea that there are still 99 more bags left to come. And you can basically just combine these two terms and it gives you some probabilistic estimate of whether or not this bag is yours, given the sensory signals you're receiving. So it's a really sort of cool way to tackle perceptual problems. And so I think what's important about this approach is that it's much more flexible than the Gestalt approach. It's necessarily probabilistic. And so if the sensory evidence that you're receiving is quite noisy, is quite ambiguous, you put more weight on your prior knowledge. If the sensory evidence that you're receiving is quite clear, you put less weight on your prior knowledge. And priors can change with experience, right? And we saw that in the last lecture when I played you that ambiguous stream of speech, right? You had no prior knowledge about what vocoded speech sounds like. You didn't understand what you heard. I gave you some prior knowledge. I played you a clear version of vocoded speech, and suddenly you could understand what you heard. So priors can change with experience. And so compared to the Gestalt approach, the Bayesian approach to perception is much more flexible. So it accounts for learning and for both and for noise in sensory systems. So let's get back to this baggage claim problem. So the first bag looks like yours. So the sensory evidence, the likelihood is telling you that it's yours. But your prior knowledge about the situation suggests that it's actually not yours, right? Because there are 99 more bags to come. And so the probability that this one bag is yours is actually very, very low. And you combine these two things together, and you come up with an estimate known as the posterior. And that simply, tells you, given the prior knowledge, your prior knowledge and the sensory signals, what's the likelihood that, in this case, the bag is mine? And if it's the first bag that's come out, you would probably conclude that it's actually not yours. Now that prior is going to change as more bags come out. So when the 86th bag comes out, it might look like yours. So again, the sensory signals, the likelihood, are saying that the bag looks like yours, it matches your bag, but your prior has changed now because you know that there actually are very few bags left to come out. So it's more likely now that this bag is yours based on this prior knowledge, and so you conclude that the bag is in fact yours. So again, the idea here is that this problem of perception is viewed as a conditional probability. Given the sensory signals I'm receiving, what's the likelihood that my belief about the world is correct? Right? Given the bag looks like mine, what's the likelihood that it actually is? And we can combine sensory information and prior knowledge together in a probabilistic way to come up with the best answer. Now, again, and I've already said this, but I'll repeat myself because I think it's important, an important aspect of this theory is that it's quite flexible. The sensory capabilities of the observer can play a role. And whether the sensory signals are noisy or not affects your final decision. Right? So if the sensory signals are quite noisy, so imagine if you're trying to decide whether there's a lion in these images. And so the sensory signals that you're receiving may suggest that there actually is a lion here. But your prior knowledge says that, in this part of the world, there are very few lions. In Wolfville, there are very few lions roaming around the streets. And so because the visual signals you're receiving are quite ambiguous, you put more weight on your prior. And so you decide, you know what? It's not a lion. As the visual signals become clearer, and you can see that down in this case here, then you put less weight on your prior knowledge. So in this case, it's pretty clear that there's a lion in that field, and so it doesn't matter that prior knowledge says there's not a lot of lions in Wolfville. You conclude that, yes, I am looking at a lion. So the quality of sensory information impacts the weight placed on prior information. The more ambiguous the sensory signals, the more you rely on prior knowledge. So there's flexibility here that we don't see under Gestalt psychology. And that's why this approach is quite nice. And I haven't gotten into the details of the math, the nitty-gritty, but the math can actually be used to predict human behavior. And in a lot of cases, it depends on the task. It's often sort of spot on and actually nicely models how we make perceptual decisions in our world. Does that mean that our brains are computing complex probabilities when we look out onto our world? Not necessarily. It just means that the math captures the behavior. The math models the behavior. The other nice thing about this approach is that you can tackle almost any perception or decision-making problem under this framework. Let's take a situation where you hear a voice on the radio, and it kind of sounds like Barack Obama, so you could frame this as a conditional probability. What's the probability that it's the president's voice, it's Obama's voice, given the acoustic information that you're receiving? So imagine somebody proposes to you, and you have to decide, should you say yes or no, right? You could cast this as a Bayesian problem. What's the probability that this person is the one, given their appearance, their personality, and their behavior? Bayesian decision-making is often used in medical diagnosis. What's the probability that this person has heart disease given a set of symptoms? Now, as I mentioned, this framework does a pretty good job at capturing how we perceive and act in our world. But we don't always think in a Bayesian way, and to point that out, I just want to end the lecture with this example that's in your textbook. And so when you're thinking about making a decision, it can actually be helpful to kind of frame it using this framework, and thinking very carefully about the sensory evidence that you have versus your prior knowledge about how the world works. And so here's an example of that. So imagine, for instance, that you've tested positive for a very serious disease. The test is 99% accurate. So you have some sensory information, right? You've tested positive for a serious disease. The test is fairly accurate, highly accurate, I would say, 99%. And so that on its own is quite scary. But if we're thinking like Bayesians, we want to apply our prior knowledge about how the world works. And so the prior knowledge in this situation is the idea that actually this disease is quite rare. So 1 in 10,000 people have the disease in the general population. So should you be worried in this case? And this is one of those cases where the Bayesian framework actually doesn't capture how we think, because most people would be worried. But in reality, most people shouldn't be worried because the disease is so rare. And if you do the math, you can work out, what's the likelihood that you actually have this disease if you've tested positive, if the test is 99% accurate, and if the disease is very, very rare, and the likelihood is less than 1%. So very, very unlikely. Now, you could throw some other information into the problem that would increase the likelihood. If you have symptoms, for instance, of disease and a positive test, well, that sort of changes the situation, right? If you have 2 positive tests, well, then your prior changes, right? Because in that case, you have some additional evidence that can factor into the formula. I'm just presenting this example to show you how sort of Bayesian decision-making can be applied in the real world, and to reinforce the point that we don't always think in this sort of optimal probabilistic way, although the Bayesian framework, as reviewed in this lecture, does capture how we perceive and act in our world to some extent. So I've come to the end of the lecture, and we'll do the lecture review. What are the 3 principles that we reviewed in this lecture of Gestalt psychology? What are the 3 principles of Gestalt psychology? Good continuation, the principle of simplicity or good form, and the principle of similarity. So good continuation suggests that lines or contours that are blocked from view are likely continuous. So if they're headed in the same direction, they're likely continuous. The principle of simplicity or good form suggests that basically the simplest solution is likely the best solution. And the principle of similarity suggests that we should group similar items together. Question 2, what is Helmholtz's likelihood principle? Question 2, what is Helmholtz's likelihood principle? It's kind of related to the Gestalt principle of good form, actually. We perceive what is most likely to have caused the pattern of stimuli on the retina. So Helmholtz is sort of starting this move towards thinking about perception in a probabilistic way. What's most likely to have caused the pattern that we see on the retina, given, that pattern and our prior knowledge about the world. Question 3, in one sentence, state the general idea behind Bayesian accounts of perception. So, in one sentence, state the general idea behind Bayesian accounts of perception. And this is really what I want you guys to understand. Again, if you didn't get any of the math, that's fine. But I want you to understand, this one single statement, because I think it's quite powerful. So perception reflects a probabilistic combination of sensory signals and prior knowledge. And what's key here is that prior knowledge can change. The weight that you place on those sensory signals can change depending on the context of the situation. So there's a lot of flexibility here. And the second thing that's key is that the answer is necessarily probabilistic. So it is, it's your best guess given the sensory signals you're receiving and your prior knowledge about how the world